I'm out here at the Lost Dog and Fox Hunters boat landing here on Lake Hanska, near Hanska, Minnesota. And today we are going to assemble a telescope. And so this is a Bresser telescope. This is the mount. It's called an equatorial mount. So we'll set things up here, and I'll explain as I go how this equatorial mount works and what an equatorial mount is. So there's several different kinds of mounts for telescopes. There's the alt-azimuth, which basically gives you side to side and up and down with different controls. And then there's the Dobsonian, which works the same way. So a telescope needs to be able to move across the horizon. So it needs to move horizontally, and also then needs to move vertically up and down, because things go along the sky on the elliptic. So that's the line for planets and the moon and so forth, generally rising in the east, going up, and then descending to the west. And so telescopes need to be able to go both back and forth, from side to side, and up and down. An equatorial mount is also a Dobsonian mount, and I'll explain a little bit more to that feature as we get things set up here. So right now I'm just getting the mount set up. Some call this a tripod, and that's appropriate. There's 3 legs, and so tripod makes sense. So get my legs adjusted. Now you'll see there's a certain way to set this up. I have this leg here always goes off to the north, and so that's about north over there. You want to be fairly accurate depending on what you are doing. If I'm just out tooling around looking at planets and things in the sky, which is most often when I'm doing astronomy, it just needs to be close to north. If I want to get more particular, then I'll actually use my compass here. And so I've got a compass, and I'll even pull it out here today. See how close I am to true north. So put my compass out here, and it says north is that way. So I'm a little bit. Well, or am I? You know what? I have a pretty good eye for true north. So looks like I'm pretty good. I'll move it a little bit, maybe like that. And so that's going to be good for most just visual observing. If we were going to do something, trip over my own work here. If we were going to do something with imaging, let's say we were going to do some imaging, then I would take this off, and I would take my reticle here, and I would also open this up here. This opens. It's been open a long time. There we go. So this opens up, and turn this. There we go. Turn this. You'd think I'd never done this before. All right, and now I can see through, and this gives me a little guide, and I line this little scope up with the North Star and a few other objects close to the North Star, and line those up perfectly. Make sure this is perfectly balanced. There's a little bubble level on this side that I can look at as well, and it gets me close enough. But for precision, you're doing astroastronomy, you want to make sure, because you actually take hundreds of frames, even with different colors. So you'll take 500 frames of Jupiter with the red color lens eyepiece in your telescope. You want to take 500 images with the blue lens in your eyepiece. You want to take another 500 images of green of Jupiter with the green filter in your eyepiece. So you have 1,500 images there, and it takes a lot of time to get 1,500 images, or maybe 3 hours in each color. And so then you'll have 3,000 images, or 1,500 of each, or whatever. In any case, you put tracking motors on this, and if it's precise, if everything is matched up precise, then all the stars are following along as your telescope is tracking it, because it's all moving, right? Well, the Earth is actually moving, but you can't just set your telescope in one place and then walk away from it. You have to have it track whatever it is you're taking the image of. You have to take many images, and you stack all those images together. You stack the blue ones, you stack the red ones, you stack the green ones, and then you have your color image of Jupiter, for example. But you need it to stay, you need each frame to have Jupiter in as much of the same place as possible. So if you have 3,000 frames of Jupiter and you stack those up, they all need to line up, not only with Jupiter, but with its moons that are visible and all the stars around it. Otherwise, it's going to be a blurry mess. So that kind of precision alignment takes this scope here, and it's very time consuming and it's a lot of work, but it's also very rewarding to have a good image. So I have my telescope more or less set up and ready for the optical tube assembly. Let's just get this a little more level here. And to be honest with you, for the most part, I don't do a lot of astrophotography. I just like to look at things in the heavens. So for me, I just use, as good a guess as I can get at north, and that's usually pretty good. And I've got my bubble level on the tripod, and I just realized I made a mistake here. I'll take this back off, and then I'm good. I don't need to have everything to be in an exact spot, and I don't mind moving both the side to side and up and down. So it's just a matter of preference and what you want to do. Let's see, where did I put my counterweight here? There we go. So with this style of telescope and this style of equatorial mount, a counterbalance is very important, and so my counterbalance then goes in here. Screw this rod in there, and this keeps everything balanced, because your telescope optical tube assembly is actually going to be in some different positions as you search the sky and find things, whether you're looking off to the north or to the west or to the south. You'll need to have your telescope balanced, whatever. I always put this one way up here. These are 9-pound counterbalances, so they're a little bit much actually, but this mount, this equatorial mount, is rated for 25 pounds, and I just like to let that one sit way down there, and then put that one up there. So, and I don't know how much this optical tube assembly weighs, but this is a good sturdy mount. So, and this probably weighs about 25 pounds. So we'll put put this up here like this. Open that up a little bit more. And sort of finger tight right now. And then we want to balance things. You want to make sure things are balanced. So I need to move this up a little bit here. We'll just lock that guy. So what you do is you basically put it like that. You see how it wants to. My counterbalances are too heavy. So to lighten those up, you just simply push them up. See, now they're too light. So we'll push this back, and it works very much like a scale, like a balance, right? So it's where you put the weight and the balance. It's windy out here today, and you wouldn't use a telescope on a windy night. I'm just doing this video to explain how to put together a telescope, and it's windy, and the wind I see is affecting whether or not this is balanced. But again, for our purposes here, close enough is good enough. So, and then let's see how my telescope, then my optical tube assembly. I see my wind is playing a big part in this here. It actually looks pretty good. That's not bad, really. So we'll keep that. Obviously, I'm not going to be looking at anything in the sky tonight, but it's a beautiful sky today. I like it when we have some clouds. So, all right. And now, usually when I'm looking at things in the sky, especially this time of the year, it's typically in the southern sky. So, I made all this fuss about, looking off to the North Star and making sure this one leg on the tripod was aligned north, and and here what I do, I look at things in the southern sky. Well, that's where all the planets are on that elliptic line, and that's where things are. So this would be a typical position early in the night. Let's say if I'm looking at Jupiter, and I would put my eyepiece in here. And I usually start out with something like a 25 millimeter eyepiece. And so this one here is a 26 millimeter eyepiece. So I'll put my 26 millimeter eyepiece in here. Now, again, people will often ask, you'll see a telescope, well, what power is that? Well, and I'll see at Walmart, Walmart will sell some cheapy telescopes. Don't buy telescopes there. And they'll have 150 power. Well, take this out, and you don't really have much. You can't determine power there. I look through here now, and I don't see much. Well, mostly because I don't have my end open here. So, it doesn't do much for me. Nothing's clear. Let's see if I can get whatever it is in focus. This is ridiculous. There's not much that can do for you. No, it doesn't even put it into focus, really. If I stand back here, actually it does. So to ask what power this is, that's an absurd question. So I'll put this 23 millimeter eyepiece in here. Now I can take. So this is a 152 millimeter refractor scope. So it's 152 millimeters from here, which is where the primary lens is. So I'll show you that. Get it around here. Okay. Oh, lose a finger there. So way down in here is where that first lens is, and this is just a dew shield. So the lens doesn't really start until about there. I see my counterweight moved on me here, so let's move that back. Let's see if it's balanced again. So I put an eyepiece back here, so that's a little heavier. That should be good. So again, as I was saying, it's 152 millimeters from here to here. Well, from here down to here, to be honest with you, 152 millimeters. So this telescope, then I take 152 divided by whatever whatever millimeter my eyepiece is, in this case a 26 millimeter eyepiece. So 152 divided by 26, and that gives me my power. That tells me the power of the telescope. Okay, so look in there and not seeing much, but some tree limbs and some budding leaves. Yeah. So I always take my glasses off too. It just feels more comfortable to put my eye close to that and focus it in. So as you can see, this is how a telescope works. So when I want to fine tune it, yeah, sure, I can look in the sky. Oh, there's Jupiter, and look at my finder scope and get it kind of close and get that close. But oh, look, I moved off the crosshair, so then I can move this, which moves it. But that's the alt, right? And this is the azimuth, right? So the side to side. Well, on this telescope, if I put tracking motors on it, once I get this set on what I'm looking at, so I get this set on Jupiter, and say that Jupiter is rising, right? And I get this piece of it here set on Jupiter, and then get this motion here set on Jupiter as well. I no longer have to move this. If I want to watch Jupiter all night long, or I could put a tracking motor on it, and I have had a tracking motor on this one, it'll just slowly keep watching, keeping aimed on Jupiter. And I don't have to touch anything. I don't have to readjust anything. I can take eyepieces out and put a new eyepiece in, and a stronger eyepiece, and it just keeps watching Jupiter. It keeps tracking Jupiter. So, or it's just handy to have that. And of course, if I don't have the motors on, then all I have to do is move this one. So I'm going to change my eyepiece out, right? And so I'll get a different eyepiece, put a new eyepiece in, and the time it took me to do that, oh look, I can't find Jupiter. Look in my finder scope here. Move this thing again. Just move that one motion, and I'm on Jupiter. So that's an equatorial mount. Once you get it set on something, you can track it all night long with only moving this part of it. You don't have to move this part of it. And actually is quite convenient, and it's especially beneficial if you're doing some imaging. So I'm going to take it down now, and this is the Bresser telescope. So it's 152 millimeters from here to here, and it is, I'm sorry, boy, that was wrong. It's 760 millimeters from here to here. So to get your power, you take 23 millimeters and divide it by 760 millimeters. It is get it around here. It is 152 millimeters here and here, right? And there's you don't have to worry about the math involved in that, but that just tells you it's a 6-inch refractor scope. So 760 millimeters from here to here, from here to here, and that gives you then, when you divide that by the size in millimeter, whether it's 23, whether it's 32, whether it's 9, it gives you the size of the power of a telescope. So 760 millimeters divided by 23 millimeters in this case.